you. So my title is different than the one that you have on your schedules because I realized, as usual, that my abstract is way too ambitious. So this will be less ambitious than the abstract says. I'm sorry for those who are disappointed. The rest of you, trust me, you will be happy. So I want to give you an introduction into chromatic homotopy theory. The philosophy of the field is that, one philosophy is that the geometry of formal group laws, formal groups, governs periodic phenomena. I should just put my word, otherwise it will become disastrous. In the stable homotopy category. Okay, so this is it's been written, I guess, two different ways, I think this was in Greg's talk and Stefan's talk, okay? And throughout this talk, I'm going to take I'm going to talk about spectra. You can learn it all from Stefan's talk, but you need to take the group to be the trivial group, which means things are going to be easier, okay? So now, there's a lot of different threads in this story. It's a very rich, complicated story. And maybe like one thread is, you start with the geometry of formal groups, and then you start talking about certain things in spectra. Another is you start talking about periodic phenomena, and then, it brings you back to the geometry of formal groups, okay? So if you were going through the periodic phenomena thread, you've talked about the work of atoms, on the alpha family, the image of J, all this stuff, and then V and self-maps and type N complexes. And then if you're going through this story, maybe you start with formal groups, and then you talk about E-theory and Landgraf exactness and things like that, okay? So I'm sure there's other stories to be told through this, but I'm gonna do, maybe this would be like the periodic phenomena side would be a more historical approach, okay? This is sort of how these things developed. But I'm gonna take more this route. This is a more algebraic route, and it's also my favorite side of the story, which is a good argument. I don't do democracy, as was clear from yesterday. I'm gonna go through this. So in this first talk, I'm gonna sort of give you some definitions, minicourse style, and then towards the end of this talk, or at the beginning of the next talk, depending on how fast I talk, or how much you slow me down, I'll give you some motivation, and then I'll start throwing in motivation through it, okay? Okay, questions before I start? Hopefully not. Sorry. I guess otherwise these are, any questions at this moment are bound to derail me. So never mind, you can ask questions later. Okay, so let me start with, first, just a definition that hasn't appeared yet. In his talk, Stefan talked about the homotopy groups, the G homotopy groups of a spectrum, okay? So I just want to use some notation. So if E is the spectrum, and in this talk, equivalently, you could have that E star, is a cohomology theory. If the spectra stuff scared you, don't like zone out right away, because if you know what a cohomology theory is, you probably won't get a lot of what I'm going to say for today. Some notation that we always use, and that I have to introduce because otherwise I'll still use it. Okay. These things all mean the same thing. Well, so this one's an isomorphism, but and then I'm just going to be using this notation. And then E minus star, and I guess one more. This is I minus star of the spectrum that represents the homology theory. Okay? So, yeah. All right. So this is notation. Whenever you see a E declared with a star and it's not eating anything, or it's eating a point or anything, these things are all just the homotopy groups of the spectrum. They're what we call the coefficients of the field. Okay? All right. So now we can start with the real definition. So maybe I'll put it on this side. All right, a multiplicative cohomology theory, E, or a homotopy ring spectrum, is called complex orientable. It's the map. So I start from the cohomology of CP infinity to the cohomology of CP1. So now this map, this is a map on cohomology. It's induced, it's the map induced by the inclusion. So CP1 includes inside CP infinity. Okay. So now we want this map to be surjective. Now, what do I mean by complex multiplicative cohomology theory? So you have cup products. So if you do a cohomology with coefficients in the ring, then you have cup products, those counts. Okay, K-theory, MU, those are multiplicative theories. So now if you have a class Y in the reduced cohomology of CP infinity in degree 2, that's not necessary, but I'll just do it here, it's fine. Such that if you do I star Y, then you're going to be in the reduced cohomology of CP1, which, let me remind us, this is S2, right? Okay. So now this is in S2. Now, by the suspension isomorphism, this is the same as E0 of S0, okay, which is the same as just E0 according to all of my notations there. Okay, so it's E0 of a point, any of these. Okay, so now this class, if this generates E star of S2, now this is, so this thing is a rank 1 module over E star, then Y is called an orientation, or a complex orientation, if you like. And as usual, if I have a theory and a choice of orientation, then I say that my thing is complex oriented instead of just orientable. Okay? All right. So there's a bit of, there's like some tricks here that you need to check, like well, that this thing is rank 1 module over E star, so that's the suspension isomorphism, and so I think maybe that's the only thing here that's maybe not.
Why is it called an orientation?
Why is it called an orientation? I don't know, because it's a choice of generator, like in if you're doing vector bundles and orientations, right? Like what's an orientation is going to be for each, like it's going to be for each of the fiber, you have a choice of generator. The fibers are rank 1, you have a choice of generator there, but really what's the orientation? It's a choice of generator, the global thing that restricts each fiber to that generator. So that's like the global thing, and those are like the fibers. So it's what's called an orientation. Okay. All right, so now examples. Okay, so the first thing you should think about in this talk when you're thinking of example is just regular cohomology. Okay, so and if R is a ring, then my rings are commutative neural rings. Okay, sometimes they're braided. I'll let you know. Okay. So then here it's not. It's just a ring. Then regular cohomology with coefficients in R. So, you know, we also write this as HR star law, okay, is complex orientable. Okay. So let's play with that example for a second. So we have H star of CP infinity with coefficients in R. Well, CP infinity has one cell in each even dimension. So for any coefficients, you just get R every other R0, and every other degree. But then, you know, the ring structure is something you can compute. You can do it using Poincare duality. That's one of the proofs uses that. Not for CP infinity, but for the CPs. And then, okay, so now this is isomorphic to, well, you can pick, so H2 is R, okay, and if you pick a generator of R as a rank 2 module, then you can pick a generator, and then you'll get that this is a polynomial algebra on Y. And what's the restriction to CP2? Well, so sorry, CP1, S2. This is R of Y modulo Y squared. Okay, so now if you think it through, well, that's definitely surjective, okay, and as long as I, you know, pick a generator here, then I'll get a generator there, okay, I'm complex oriented. Okay. So, another example, is one that I won't go through because it'll be the content of the problem session, so complex K-theory. That's sort of the second cohomology theory that we learned about. Complex K-theory, KU, is complex orientable. So this will happen in the problem session. And I'll throw another example out there. MU is complex orientable. And we're going to talk a lot about MU, but the key for this is to realize that CP infinity is equivalent to, well, okay, so CP infinity is equivalent to BU1, maybe that's not a surprise, okay? So CP infinity classifies complex line bundles, okay, these are, you know, equivalent to principal U1 bundles, okay? But the thing to realize is that, in fact, the first Tom space, so the first space of the spectrum for CP infinity, which I guess the first, maybe it's not the first space, it's the second one, is MU1 that it's actually equivalent to MU1, okay? And then there's a map from MU2 of CP infinity into MU1. So you just pick an equivalence and there is a complex orientation. So that's great, those are examples. So what are non-examples? I did not lose the board. Okay. One example is KO is a classic example of non-example. Okay, but we're going to talk about the examples mostly, so I'll stick to those. So now, okay, so what is motivation? So why? So one reason that you might study these is, well, what's this? So let's just take R is equal to, let's take R is equal to Z and this, right? Then an example of a Y is to take the first Chern class of, maybe I should make a definition, so because I'll talk about this thing up again. So, sorry, I'm going to finish that thought. But I'm going to let gamma over CP infinity be the tautological line bundle. Line bundle. And I guess later I'll let, so top one, be the trivial one. Okay, so then what's a choice of Y? You can take the first Chern class. of that line bundle. So this is the first Chern class. Chern class. Okay, so like why do we care? So it turns out that, and I won't go much more into that, although I think problem session will talk more about this, is that complex orientable theories have a natural theory of Chern classes. Okay. So I've only told you something about CP infinity, so you might be like, oh, well, wait a second, like those are just line bundles, but there's the splitting principle, right? So if I know everything, if I can define Chern classes on line bundles, then by the splitting principle, I can do it on other bundles. And so there's going to be maybe more, actually, maybe I don't know, but there's going to be something related to this that happens in the problem session. In fact, I think they're going to discuss more this lemma. Okay. So this is one reason to care about this. Obviously, you want to study vector bundles, maybe classical Chern classes don't give you enough. Then you have all these theories that you can just test your Chern class and then study your vector bundles. But here, okay, so here's a fact about complex orientable theories. If E, okay, let EY be a complex oriented theory. Okay, so now let's let PI be the map. So I can take a bunch of a product of CP infinities, so n times to CP infinity. So this is the ith projection. Okay. And then let's let y sub I be the pullback of your orientation. Okay, so in cohomology, so yi is in the cohomology of CP infinity n times with itself. Okay, well then this cohomology that y sub I lives in is actually isomorphic to E star, so the coefficient ring, adjoin all of these classes that I just. And okay, so how do you prove this? Well, the proof I know, it's the one in the blue book, is you use the Atiyah-Hirzebruch spectral sequence. And I won't say more about that because I think they're going to talk about this for K-theory in the problem session. Spectral sequence. Okay, so that's one way to do it. Okay. So you just ask for surjectivity of one map and you get this big structure results called the cohomology of all the CP infinities. You can actually get the cohomology of the VUNs also, which maybe suggests to you why you have the theory of Chern classes. It's going to be E star, adjoin Chern, your general Chern classes, and then you can pull those back. Okay, so then that lets me get to the next definition. So here I talked about projection maps from products of CP infinities to itself. There's another really important map that involves CP infinities and its product. So I'm going to let mu from CP infinity times CP infinity now to itself be the H space multiplication. Okay, so let's see. Everybody's going to have a favorite way to think about this map, but here's one way. CP infinity is BU1, right? Okay. So U1 is an abelian group. So if I do U1 cross U1 to U1, right, that's a group homomorphism, just a group multiplication, because it's abelian, okay? So then I can be this, and then I get a model that is not B. Okay?
Sorry, could I just ask something basic about the lemma? I'm confused. So, for example, if I take ordinary cohomology and n equals to 1, isn't it true that the cohomology of just CP infinity is not a power series ring, but just an ordinary?
Great question. This is the test question. Is the audience listening? Because if they are, if somebody's listening, somebody asked this question. So I failed to slide it under the rug. So, okay, no, it's a good question. So it's a question of definition here. It's what do I mean by this power series ring, okay? And what I mean is degree-wise completion. So what I mean by this, yeah. So what I mean by this is E star adjoint X modulo X to the N, and then I take the degree I part, and then I take the inverse image.
Okay.
Okay? And if you work that out, because cohomology theory there's nothing in negative degrees or anything. If you complete degree rise, you're not going to get anything. The completion's really not going to do anything. But you're used to this lie. I mean, like, if you teach cohomology, algebraic topology, like, it's really hard to get the students to buy into this. Because they're like, what about y plus y squared, right? So we're all used to this lie, but yeah, I've extended it, okay? But that's a good question.
Yeah, good, thanks. This helps.
All right, so now, let's see. Let me just record this as degree-wise completion. All right. I don't know if I'm putting this high enough for people in the back. It's hard. Okay, so now, so that means that I can, so I again have a map on cohomology, but now it goes from CP infinity to CP infinity cross CP infinity. Okay. So I can take my complex orientation and it's going to go to some class. Okay. But now this class is something in a power series ring on two variables, right? So it's a power series, so I'm going to call F sub, I'm going to give it two names. So the first name is suggestive that, you know, how we like to denote power series. Okay. The second name I'm going to give it is y1 plus over e, and sometimes I'll write plus over fe if I don't have a theory later, okay? I'm just going to be very relaxed with this notation, but I think you'll always know who I'm talking about. y1 plus over e of y2, okay? So maybe you're like, ugh, what does that mean? It means that, okay? That's it. It's just notation, all right? Okay, so but then, you know, this notation is extremely suggestive, so, you know, it would be bad notation if, for example, it wasn't equal to y2 plus over e with y1, right? Because, you know, plus we know to be commutative. So, or we've accepted as a convention among all of us that we should only use plus if it's commutative. Okay, so what's the reason? So that this is good notation. Here, on this map here, this classifies the tensor product of line bundles. Okay, so suppose I pull back the tautological line bundle, what I get is something that's isomorphic to, I could take the first projection and pull back gamma along that, or I could take the second projection and pull back gamma along that, okay? And, you know, I think, I don't know if it'll come back, but I might call this gamma 1 and gamma 2, okay? And so basically, and if you have two bundles and you want to take their tensor product, well, you can have one bundle over there going into, you use one of the bundles to map into one of the copies and the other one to map in the other copies, and then you pull back, and then you get the tensor product. So this thing classifies the tensor product of line bundles. But okay, the tensor product of line bundles has lots of nice properties. Oh, right, I'm not supposed to do that. I think if I wet it more, it would solve this problem, but then it would also create a sea of chalky water. I'm sorry, all the Germans in the room. You have to watch me do that. And Paul, because he does this well too. Okay, so what are properties that we know about the tensor product of line bundles? Well, okay, everything I'm going to say is going to be up to isomorphism. Okay, well, it's associative, it's commutative, it's unitable. So with unit, the trivial bundle, okay, and it has inverse, right? So just a linear dual finalist. Okay. So this reflects into so if, from this it follows that the power series y1 plus y2 satisfies, well, y1 plus y2 plus if you take in a third variable, that's equal to y1 plus y2 plus y3. And the one that we agreed was desirable is commutative. See, if I so what's the, so I'll say that in a second. So sorry, so y1 plus e of 0 is just, or y plus e of 0. So if I plug in 0 in my variable, I get y. So if I do it in the other variable using that, I also get y. And the last one is there exists some series, which I'll write as this notation. Okay, so this is in e star on one variable, such that, well, this will act as an inverse. So -1 e of y plus e of y is, and it's two-sided. Okay, so this one is actually not necessary. You can deduce it from the other ones, but but like all these properties now make this definition feel natural. So power series F of y1, y2 in R, y1, y2 is called the formal group law. Formal group law if it satisfies A through D. Okay, so the kind of examples, well, the first example that we have is the HR, okay? So we're going to take, let's just do Z. Okay, so then we can use, naturality to get it in for any R, but so let's pick, again, let's pick our Y to be the first third class of gamma, okay? So that's in H2. Okay. Then mu star of Y then is going to be the first third class of gamma 1 tensor gamma 2. which is equal to C1 gamma 1 plus C1 gamma 2, which is, if you trace things through, A1 plus 1, 2. Okay? So, all right, there's various ways you can convince yourself of that. You don't have to go through Chern classes. You can actually just compute that that's what's happening with the projections. Okay, so from this example, we see that, so what is this power series? So then this is, sorry, I meant to finish it. Now this is the formal root law for HC. It's very boring, it's just sum, okay, that's the easiest example. The other ones are not boring. K-theory maybe is like a little fancier, and then after that, these are really power series. They're not, I don't know any other example that is actually a polynomial okay? But what is, so what is this telling us is that, so from this we get that if I take Fe of, and I plug in Chern class for two, like E Chern classes for two line bundles, then this is telling me what the E Chern class of their tensor product is. So that's what the formal root law is. It's the formula for how do you compute the Chern class of a tensor product, okay? Well, you plug it into this power series and you get something, okay? And in here, it's easy, it's addition. Okay, so, and then in the problem session, you'll do the K-theory example. Okay? In one of the problem sessions. Okay, so now problem session. K-theory is going to be in the problem session. Okay, so my third example, right, was mu. Okay, so mu is like a big theorem. Okay, so there's a theorem of Quillen. Is that the formal root law of mu is canonically isomorphic to the universal formal root law. Maybe, I shouldn't say canonically here, is, oh, I didn't need to erase all that. Oh, well, is isomorphic to the universal formal root law. Okay, I'll tell you what that means. And mu star is isomorphic to the Lazard. Okay. So if you know what these things are, great, but if you know what these things are, probably you already know the rest of everything that I told you. So I'm going to tell you like what I mean by the statement, okay? So given a, and then I'm going to throw in some adjectives, but they're just so I'm not making a wrong statement. So given a homogeneous formal root law.
I thought this much was due to common authority.
You mean Connor Floyd proved that it's that, but Quillen gave some kind of naturality?
Yeah, he shows it.
I thought it was Quillen, but it could be that I'm, so, I'm happy to add some.
I think it's Quillen.
But it's okay. All right, so the statement is given a we can check after. Given a homogeneous formal root law F over a graded ring R, and this is where I'm just putting my adjectives, graded ring R, and then I'll write L star, so it's clear that it's graded. So there is a ring homomorphism. Phi from mu star to R star, such that, and now I need a new board. there's a lot of suspense, right? But maybe you know. Okay, so if I do, okay, so I'm going to make a definition as I write. So this phi star of mu of y1, y2, that's going to be, okay, so the formal group law of mu is it's some power series, right? So I'm going to be glib about it. Okay, so that's what power series and two variables look like. So the definition of this is you apply phi, well, to the power series just by applying it to the coefficients. Okay, y1 to the I, y2 to the j. And and then the statement now, we're ready for it, is that this is equal to f, y1, y2, for the formal group law over R that you have. Okay? So if you have a formal group law over some other ring, well, you just kind of find a ring homomorphism that does the right thing to the coefficients. Okay? And then you're good. Okay. And so in particular, this comment about the Lazard ring. So the universal formal group law lives over this ring called the Lazard ring, and a priori, like, what is this ring? So maybe, so where do these coefficients live over? Well, you know, you add them to Z, okay? And then you impose a bunch of relations, the ones you need for all the conditions that you did to hold, right? Okay? So this is like, you know, abstractly, this has to be mu star if it's over the Lazard ring. But that's nasty, like, there's a lot of this. And the big theorem of Lazard is that the universal formal group law actually lives over a polynomial ring, okay? So instead of having a bunch of these, I have other variables, oops. These xi are in degree 2i for mu. Okay. And you know, the aij's then are polynomials in these things. Okay. So in particular, mu star has to be that, and there isn't, so I'm not going to write down the formal group law of mu, but just to like give you like a flavor, like, so because it's a formal group law, it's going to have to start like this, okay? And if you sort of work things out, you'll get that you know, you can pick x1 so that it's the first coefficients of x, y1, y2, but this is where I'll stop trying to give you a hint. Okay, so it is a power series, you know, this doesn't have a finite truncation. Well, I mean, it has, but they're not equal. Okay. So mu is the queen of all the formal, holds the queen of all the formal group laws. This sort of this is like the first hint of like how important it's going to be to studying stable homotopy theory. That means that if you want a theory of Chern classes, well, really, it comes from mu in some sort of fundamental sense. All right, so now I've told you about formal group laws. So I've told you about objects, but like what are the morphisms, right? So let's make a definition. So suppose that I have two formal group laws. Over ring R, okay? And so then a morphism F from F to G is a power series. So f of x in, I guess I should use y. So there's a reason why I'm not using x as my variable. It's because these are like what people call the colors, and then yeah, well, makes it difficult for me, but all right. So you have a power series f of x and f of y in there, such that, well, okay, so this notation makes it really easy to describe what it has. Well, it's a morphism of something formal group law, so you just copy what it should look like for groups. Okay, so this is where I said I would, sometimes if I didn't have a theory around, I would just use f. So this is my definition of this notation. So f of y1 plus g f of y1. Okay, so we're gonna let end R of f be all endomorphisms, and ought sub R of f all isomorphisms of the formal group law. Okay, and there's an example, a canonical example. So take any n in z, and let's start with n greater or equal to 0. Okay, then there's an example of an endomorphism, which we tend to write like this, and it's just you just add y to itself n times. So in other words, you compose the series with itself n times. Okay? And now if n is less than 0, let me use this corner. If n is less than 0, then you can still define a series by just composing the -1 series with minus n, with the thing we just defined. Okay. So you just use the inverse, okay, the obvious thing that you can do. Okay. So we get some kind of function from z to end R of f. And it turns out, well, okay, so it's not any kind of function, it's a ring homomorphism, so this is actually a ring. Okay. So the addition here is you always have to use, whenever you want to do the obvious thing, you always have to use the F addition, okay, and composition gives you the addition, okay, and the unit is just the series X. Okay.
On the right, you mean y. On the right, for the negative one.
I do mean Y. I'm struggling. Yeah, okay. I was doing so good. Y. I always mean Y. When I write X, I always mean Y. Except when I write X. I got to here and I wrote this with X1 and X2, and then I got stuck, and then I had to change all my X's to Y. So my brain wants them to be X's. Okay, so okay, so now another definition. All right, so fix a prime p. And all right, yeah. And then we're going to let vi be equal to x to the p to the I minus 1. So this is in, and I'm going to take mu star, and so this is going to be in degree 2 times p to the I minus 1, okay? So this is one of the x's that I have up there, okay? And really, it's more natural to think of it now. Since I fixed the prime, we can localize it p, so I'm gonna invert all primes that are not p. So that's gonna be the name of an element in mu star. And maybe like the remark, so why these, is that if I look at the p series of mu, here, if I have a theory, I'll just call it that, then it's gonna look like, it's gonna be equivalent to vi x to the y, to the p to the I modulo p v1 v I minus 1. Oh, that's not right. Sorry. I need to kill more. Let me just write it this way. It's gonna be, so modulo p and then all the xi's where I is less than, sorry, too many i's, k is less than p to the I minus 1. So if you mod out by all the previous generators, okay, then you're gonna get that this is gonna be the leading term, and I just meant the leading term, so it costs out. Okay? So these xi, like if you mod out by stuff that's of lower degrees, they're the coefficients of the pth power in the pth series. Okay? And then, so now we're ready to make one of the really important definitions is a formal group law F over an FP algebra R has, so height H, and then the H is going to be, yeah, H, if for the map phi from mu star to R star classifying F phi of vi is equal to 0 if I is less than H, and it's going to be a unit in R if I is equal to H. And I'm going to say, I'm also going to write V0 to V. Okay? That's going to be the convention. Okay, then we're going to have, so what if phi vi is 0 for all I? Then we're going to say that, then F, we're going to say that it has height infinity. And we're going to extend the definition. If R is a QP algebra, or sorry, a Q algebra, just a rational vector space, then we're going to say that F has height 0. Okay? And let's look at examples. If I do HFP, okay? Now, if I look, that's the regular cohomology with FP coefficients. The P series of HFP, well, so the formal group law for this was just normal addition, okay? And the P series is use your funny addition and do it P times. So I'm just going to get x plus x plus x P times. So that's Px, which is 0 over Fp, okay? So this has height infinity. And then if I do HQ, then I have the same formula, but a different conclusion. And of course, I mean y, but it's okay. Okay, we're all mathematicians, we can use this. Okay, so P of x, but now P is non-zero. In fact, it's a unit, so this has height infinity. Okay, but then there's all this in-between notion of, oops, yeah, thank you. There's all this in-between notion between 0 and infinity that don't have the funny definitions that I'm not doing an example of. Well, if you do mod PK theory, then this is going to have height 1, and this is the problem session, right? I've kept K theory for the problem. Okay, so that's going to be an example. The other ones, well, I'm going to write a theorem. Okay, so I mean, there's various things that could happen. It could be that, yeah, okay, you have formal group laws at all the primes, you can build a formal group law of all the heights. True. But then you could ask, oh, well, what about complex oriented cohomology theory that have those as formal group laws? That would be more difficult. Still true. Okay, so let me write the big theorem. Okay, so this one I don't know. Well, I guess I didn't. I don't even have, like, this one it's hard to figure out, like, whose name to put on. So people can, probably because it's combining different things. So, okay, that at every prime there's a formal group law of the height that you want. That's an algebraic result. That's a theorem. Like Honda constructed these, okay? And people call them often, certain choices, they call them the Honda formal group laws, okay? So for certain choices of these examples, you can find the proof in Hausdorff's theory of formal groups. So now there's a statement that these can be generalized, and all right, so theorem from the good old days. So we're going to fix a prime P and some h greater or equal to 1, okay, less than infinity, just some actual number. So then there exists, so how would I do this? Right. So, okay, so we're going to define K of h. I'm going to write something. So I'm going to take mu, okay, and actually I'm going to localize it at P. I'm going to talk about P localization in my next lecture, okay? But you know, right now I'm going to do a bunch of things and I want you to think, okay, Stefan's teaching me about spectra, and he's teaching me about the smash product, and he's going to do all kinds of algebra with it, right? So in spectra, you can do, it turns out, now that we have all these nice model of spectra, you can do things like in quotients, treat things like rings and whatnot. And mu is like a very nice ring in this category, so you can do fun things with it, okay? So one thing you can do is you can invert this VH. And then we're going to kill everything okay, all the other generators, okay? So you can do this in Spectral and you get a spectrum, K of H, okay? Then this is called the H Morava K-theory. Okay. So, and some properties. So, its homotopy groups are just what, if you think about what's left from the mu ring, you're going to get this, okay? And the formal group law, it's going to look like, well, because of the fact I told you about these things, it's going to be VH P to the H minus 1, P to the H plus higher order terms. Okay, so maybe you're used to seeing no higher order terms, but I was pretty glib about my choice of generators. You can pick your generators, and you can do this where you don't even need higher order terms, okay? But that would get more technical. So in particular, has height H. I wanted to say this is called Morava, maybe 0 is that K is complex oriented. All right. Okay, so these are called the Morava K-theories, so I feel like Morava has something to do with their conception. The fact that the caves were built in a less sort of nice way, maybe nice is not the right word, but like it was maybe more difficult to construct them before. And somebody constructed them using the Bach-Sullivan construction, and I cannot find the name of who it is. So if somebody knows, what are you tell me? I don't know. Okay, I couldn't find it. Maybe Johnson Whistler. That was my best guess, given what people were saying in the literature. And then once EKMM spectra came out, there's a chapter on EKMM spectra about doing things to NU, and then you could just get them straight like that once you have the theory set up. Okay? EKMM is one of the models of spectra that Stefan is not telling us about. And then, okay, so now these are really, really important. Okay, so now my lecture was to sort of not just tell you there are some theories and they do that. Like there are some theories they do this, they have really nice properties. So one thing that they do is that the KAs have Kuhn isomorphisms. Isomorphism. And any theory that has a Kuhn isomorphism is a wedge of suspension of these things. Okay? So because of that, they call them the fields. Or the prime fields, right? There's other fields, but these are like the prime fields. There's more to that statement, but I don't think I'm going to be that person, so I'm not going to have time to tell you. But maybe like the example that I want to say is that Morava K-theory is a wedge of suspensions of K1, of the first Morava K-theory. Okay, so we said earlier this at height 1, it's a wedge of suspensions of these things. And for all practical purposes going forward, you can forget the difference. If you want, you can just think that K-theory is K1. The only thing you'll have to delete is this word prime, because it's a wedge of suspensions of it, okay? But all the other kinds of things I'm gonna say, you might as well think of K1 as Morava K-theory, okay?
Wait, could I just ask a question?
Yeah.
So you see that there's no way that if I have a spectrum which is not a field spectrum, that the Kuhn spectrum will not collapse to give me the Kuhn isomorphism? If you are a field spectrum, then you must have the full Kuhn isomorphism, then your wedge suspension of these. But could you have a theory that still had the Kuhn iso, but it's not a field spectrum?
I think the answer is no. The
spectrum could collapse. Or
Can you ask me afterwards? Can we talk? I'm getting confused. Yeah. Right, because I cannot think on my feet when there's a camera pointing at me and a lot of faces. So I will answer you in a minute. Okay, so then I think that this is all I have time to do. So the next time I'll start with connecting with Greg's lectures with the Balmer spectrum. So these are going to be the key ones for that. Okay, so that's it for now.